So now we're going to talk about square root rules, and square root rules apply really to any roots, but we're focusing on square roots, and a lot of this has to do with notation. So the first root here is basically the first rule is just explaining notation. It's letting you know that when you have a number beside a square root, that there's understood multiplication between them. So for example, 2 times the square root of 9, we're going to be using our order of operations. And with our order of operations, where parentheses is, we also have absolute value there, and we now are going to have square root there. So whatever occurs under a square root symbol, you do first in your order of operations. So here we would take the square root of 9 and get 3 as the first step. So we end up with 2 times 3, which is 6. Now in the next problem, we have 3 times the square root of 5. We cannot take the square root of 5. It's not a perfect square. Therefore, the answer is 3 times the square root of 5. In other words, we don't do anything to it because we can't take the square root of 5, so there's nothing to multiply 3 times except the square root of 5. The next rule is just again referring to notation. It lets you know that when you have a negative symbol in front of a square root, it means the opposite. So in this example, you would just find the square root of 144, which is 12, and then you would put the negative symbol in front of it because it means the opposite of 12, which is negative 12. So now we're going to talk about the rules for multiplying when you're working with square roots. So one rule that's really important to know is that if you have the square root of x times the square root of y, it equals the same thing as the square root of x times y underneath the square root symbol. Now what's different about these two is your order of operations. So if we look at the first one, the square root of x times the square root of y, here we would actually complete our square root first. We would take our square root first and then we would multiply. In the second example, we would actually multiply first, since all that's under our square root, and then take the square root. But what we're going to find is either way, you get the same answer, which is different for addition. So you need to understand the order of operations. So the square root of 4 times the square root of 9, by order of operations, you would have to take the square root first. So you would get 2 times 3, which is 6. Versus the square root of 4 times 9 under the square root symbol. So in that example, you multiply first because you have to do what's under your square root symbol first. Then you take the square root, but you still get 6. So the notation means something different in each of these examples as far as your order of operations, but you'll get the same answer. Okay? So now we have another example. We have the square root of 25 times the square root of 4. The square root of 25 is 5, square root of 4 is 2, and 5 times 2 is 10. So again, your order of operations is asking you to take the square root first and then multiply. Versus the next one, which the order of operations would be to multiply first because that's what's under the square root, and square root trumps everything. It tells you to do that first. We take the square root of 100, which gives you 10. Again, you'll notice that regardless of our order of operations, we end up with the same answer. In the next example, we have the square root of 16 times the square root of 4. Square root of 16 is 4, square root of 4 is 2, so that gives us 8. Now, the example after this is a great example of where using this rule that we just learned, that it doesn't matter if you break them up or multiply first or take the square root first. It doesn't matter which one you do first, you're going to get the same answer. Well, maybe I don't know what 16 times 4 is. It's 64. But if you don't know that, then it may be easier just to break this up and do the square root of 16 times the square root of 4 like we did in our previous problem, which will give us 8. If we had done it the way that the order of operations tells us to do it, we would have ended up with the square root of 64, which is 8. But it's nice to know that we have this property that tells us those are the same. Our order of operation will give us the same answer regardless of which way we do it, so that when we're working with the math, we can make the math easier on ourselves. Then there's the next example. In the next example, it is essential that we know this rule because you can't take the square root of 2 and you can't take the square root of 8. The square root of 2, there's no number times itself that equals 2, right? It's prime, actually. Square root of 8 is not prime, but there's no number times itself that equals 8. No whole number. So you can't take the square roots of those. But since we know that that equals this, right? We know that that equals this by the property we just learned. We can take the square root of 16, which is 4. Now the next rule is for addition. Now with addition, taking the square roots first versus adding first does make a difference in your answer. So you do need to understand the order of operations and what the notation means. So let's look at our first example. The square root of 9 is 3, and the square root of 25 is 5. So the way that notation reads, we have to take the square root first and then we add, because you always do what's under the square root first. We get 8. Then we have the square root of 9 plus 25 under the square root. So we have to add first, since all of that is under the square root, and you always do your square root first. So we get the square root of 34, which is the square root of 34. We can't take the square root of 34, right? Because there's no number times itself that are whole numbers to give us 34. But we can compare these. I mean, obviously they're not equal, right? Because 8 does not equal the square root of 34. So we can compare them. So what is a perfect square that's really close to 34? 36 is a perfect square that's really close to 34. So if I take the square root of 36, that equals 6. So the square root of 9 plus the square root of 25 just equals 34. That's the answer. But what if I was to ask you something like this? Tell me greater than, less than, or equal to. With those two problems. Well, you would do your work and you'd figure out that this equals 8, this side equals 8, and this side equals the square root of 34. And this side equals the square root of 34. So you could approximate which one's bigger, because this is around 6. It's actually a little bit smaller than 6, but it's around 6. So we could say greater than. That the left problem is greater than the right problem. Okay? Next one. In the next example, the square root of 4 equals 2, and the square root of 64 equals 8, so that equals 10. The last problem, we have to add before we take the square root, and we get 68. And we can't take the square root of that, right? That's not a perfect square. So you can obviously tell these do not equal each other. But let's approximate. Let's a very close perfect square root of 68. 64 is really close to 68. So we can approximate if we're asked to. You may not be asked to, but we can. And so we know that this is close to 8. It's actually a little bit bigger than 8. So we know that this first problem here is larger than the second problem here, the solution to the second problem. So we have a couple of more properties that actually talk about the inverse of square and square rooting. So when we talk about inverse properties, think about, let's start with adding. The inverse of adding a positive is adding a negative. The inverse of multiplying, you multiply reciprocals. The inverse operation to squaring is square rooting. So if I'm square rooting a 4, the inverse operation would be to square it, and that'll give me 4. If I'm squaring a 4, the inverse operation is to take a square root, and that'll give me a 4. And we'll be using this property when we solve equations. So we're now going to see these properties with numbers 5 and 6. So with number 5, what it's actually telling you there is to find the square root of x squared. So let's use some numbers to see how this works out. So by order of operations, the square root of 4 squared means that we would square that 4. By order of operations, we do what's under the square root first, and then we take the square root, so we get 4. So this shows you that when you have a square root and a square, they actually cancel each other, and you're left with whatever's underneath your square root, the 4. So that's what we're seeing in our rule. Up here, the square root of x squared, the square and the square root cancel, and you're left with x. The same thing occurs if the square root is outside of your square root. So it could be written outside of the parentheses, like beside number 6, or it could be written like this. They both mean the same thing. Both of those notations mean the same thing. And let's look at an example. So with order of operations, this notation means the square root of 4 multiplied twice. By order of operations, you take the square root of 4, and then you'd multiply. So either way, you end up with 4, the number that's under your square root symbol. So the square and the square root cancel each other. So squares and square roots are inverse operations of each other. They cancel each other. All right, so first problem. This is 6 times the square root of 16. So we take the square root of 16 as our first step by order of operations, and then we multiply, so we get 24. And the next one, we're going to take the square root of each of those and then multiply by order of operations. So that's 7 times 2, which is 14. So the next one, now here is where knowing our property is very helpful. I don't know about you all, but I don't really want to do 144 times 64, and I know that this is the same thing as taking the square roots individually by that property we learned, and then multiplying. So I'm going to do it this way, because that's a whole lot easier. And that gives me 96. Okay? All right. Now with addition, we cannot break that up. So we cannot do the square root of 100 plus the square root of 81. You cannot do that. It is not equal to this. So all we can do here is add. So we get the square root of 181. Well, the square root of 181 is not a perfect square. There's not 2 whole numbers that equal one, or not 2. There's not one whole number that when multiplied by itself equals 181. Therefore, we can't take the square root. Therefore, that is the answer. The square root of 9 squared is 9, because square roots and squares cancel each other. The square root of 121 squared is 121, because square roots and squares cancel each other. So now we're going to talk about approximating square roots. So basically, when you're given a square root and it's not a perfect square, you can't take the square root of it. But you can figure out what 2 integers it lies between, or what 2 numbers it lies between. So we're going to start by looking at the square root of 8 as our example. So what you do is you think about the 2 perfect squares that 8 is closest to. So I don't know about you, but my mind automatically goes to 9, because that's a really close perfect square. So I know that the square root of 8 is going to be less than the square root of 9. And the square root of 9 is 3. So if I have 3 as the first the first square root bigger than 8, I know that 2 is going to be my first square root less than 8. So I can put a square root of 4 there. Therefore, the square root of 8 lies between 2 and 3. And this would be the answer to a problem that says approximate the square root of 8 by writing the integers it lies between. And you use the less than symbols to do that. So I have a couple of examples I'm going to do. So the square root of 39 is really close to, be thinking this to yourself, 36. And we know that that's 6 squared, so the next one's going to be 7 squared, so that's 49. And 39 lies between them. Therefore, the square root of 39 is greater than 6 and less than 7. For 18, the square root of 18, if we think about the perfect squares that are close to that, I automatically think 25. And then that's 5 squared, so 4 squared is going to be 16. So it lies between 25, the square root of 25 and the square root of 16. And you take those square roots that you can of the perfect squares, and 4 is less than the square root of 18, which is less than 5. And that's your answer. The next one's 107. 107, I automatically think of 100, which is smaller than it, and so that's 10 squared, and then 11 squared would be the next one, which is 121. So that's how you approximate when you get square roots that are not perfect squares.